Hi, my name is Brian Caffo, and I'm in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. This is the Generalized Linear Models class of the Regression Models class. This course is taught with my co-instructors, Jeff Leake and Roger Pang. Like I said, we're all in the Department of Biostatistics at the Bloomberg School of Public Health. Okay, so linear models, to me, other people might dispute this, but to me, are the single most useful applied statistical technique. But it's not like they're limitation free. So a couple of limitations that come to my mind. First of all, additive response models don't make much sense if the response is discrete. If it's 0, 1, then it doesn't make as much sense, or even if they're strictly positive. Additive error models often don't make sense. For example, if the outcome has to be positive, and the error is both positive or negative, you add the error and you could possibly get negative responses from the model when the observed data can never be negative. You can do things like transformations, but often transformations are hard to interpret. I think there's an actual value to modeling the data on the scale that it was collected, or the scale that's of interest. And then, particularly interpretable transformations, natural log being the most obvious one, isn't applicable to negative or 0 values. And you can get around that, of course, but you're then no longer have natural log. You have natural log of some function of the data. So GLMs are generalized linear models. They're introduced in a 1972 RSSB paper by Nelder and Wedderburn. And the GLM involves 3 components. There's a so-called exponential family model for the response, a systematic component via a linear predictor, and then a link function that connects the means of the response to the linear predictor. And we'll go through all 3 parts, but now you know what a GLM is in terms of its definition. It has to have those 3 things, but we'll go through the specifics of what they are.